So what am I going to make here? Ooh, 10 people on Zoom. We're doing it. So what am I going to add? A what and a what? I'm hopefully going to add a bromine and an alcohol, right? A Br and an OH. And this is going to be an anti-addition. So bromine on one side, OH on the other, right? We don't know absolute stereochemistry, but we know relative to each other, they're on opposite sides. All right, so I'm going to add chlorine and OH. Which carbon gets the OH? Which carbon gets the chlorine? Carbon A gets the OH. So you end up with OH and Cl. But I appreciate you putting yourself out there. So I was going to tell you why that is. So if you remember the mechanism, right, we make a chloronium ion, right, we get to something that's going to look like this. So you make your chloronium ion, right? And we have to figure out which carbon is more positive, right? Which one can best handle having a positive charge? Because the more positive carbon is the carbon your nucleophile wants to add to, right? Nucleophiles always want to add to the most positive thing they can. So we could say, hey, what happens if we break this bond, right? We get this carbocation. What happens if we break this bond? We would make that carbocation. Which carbocation is better? You did the same thing the person in the early class did. You just pointed at the screen. Like, I can't tell. It's just like, the blue one's the bad one. Primary carbocation bad. Tertiary carbocation good. She did the same thing. I was pointing the one, I did the top and bottom. She's like, I was pointing the one on top. And I was like, how can I tell? I don't know. All right. So tertiary carbocations are better than primary carbocations. So the carbon in the chloronium ion that's most positive is the one that can make the most stable positive charge. So this carbon here is more positive than the blue carbon. So your nucleophile, which is your water, when it's deciding which of the two carbons to add to, it depicts to add to the one that is most positive. So it goes like, oh, the green carbon is more positive than the blue carbon. So I'm going to add to the green carbon because I'm attracted to positive things. That makes sense? So whenever you look at your chloronium ion, you're just going to say like, okay, which of the two carbons is more substituted? Because then that carbon can better stabilize positive charge. That's the carbon I'm going to add my oxygen to because it's more positive. Where's my oxygen going to go? A, right? And again, this is an anti-addition. So I have to say that if my oxygen, let's say I put my oxygen up, that means the bromine has to be on the opposite side from that oxygen, so it's back. And then this methyl group, right there, if my oxygen is up, that means the other group, okay, so methyl group has to be back. So you still keep the two carbons in plane, a wedge and a dash. So like today, I've had one full section between the two sections. I think I've hit 40 people now total for the day. What are we doing? Tongy should be closed. We should not be hungover from the coop. It should not be happening. We should be at home, not getting the Rona. Not being like, woo, I don't have to go to class. All right. So, this feel good? Seems all right? So now we're going to do something that's mechanistically similar, which is an oxymercuration. So this is basically doing a hydration that doesn't form a carbocation. So the good news about that is there are no rearrangements, right? So you basically just get to follow Markovnikov's rule, put the hydrogen on the least substituted carbon, put the oxygen that you're adding on the most substituted carbon. Nothing tricky. That's good news. The bad news this reaction uses mercury, and mercury is very bad for you. So this is where I give you the first real insight into the brain of an organic chemist. If you gave me a bottle that said on it liquid death, but it got my yield from 80% to 95%, I'd be like, I guess I have to wear 2 pair of gloves because I have to use this all the time now, right? We're like, if I can get my yield up, who cares about my 70s? I don't really care. Well, 95% yield, but I'm done at 63? Yeah, those were diaper years. I'm fine. I don't need those, right? So it works, but we have to use mercury, which is not good for you. But what matters is it works. All right. So this reaction occurs in 2 steps. So you take your alkene, and I'm not going to have enough space. Should just settle into that right now. So you take mercury, acetate, water. So that's mercury, parenthesis, OAC, close parenthesis, 2. Water, and THF. And then the second step is you add sodium borohydride and hydroxide. So this is a 2-step reaction, which means the reagents in step 1 never see the reagents in step 2. So you do step 1, you isolate the product you make from step 1, remove everything but that product, and then add the reagents for step 2. So you're basically doing 2 completely totally different reactions. What you end up with is just putting the alcohol on the most substituted carbon of your double bond. Right? So the reason we need this reagent to be able to do this is if we took our exact same starting material and we used water and sulfuric acid, right? We wouldn't put our alcohol on this carbon, right? Our alcohol would end up over there because we would make a carbocation, it would rearrange. So we need to have a reagent that doesn't lead to rearrangement. Something I want to point out real quick, THF here. Oops. So this solvent, this THF is solvent, it's not in the mechanism. Solvents are typically just things that are going to dissolve your reagents. so that they can have a place to react, right? Because I can't just pile a bunch of solids together. They don't mix, right? So I have to have something to dissolve everything up. And that's what the role of a solvent is. And oftentimes they don't come into the actual mechanism. They're just something that dissolves everything, but then just like is there, but doesn't participate, right? So like when we do this mechanism, THF never shows up in the mechanism. It's not because I forgot it. It's because it just doesn't do anything. It just dissolves everything. So I have this abbreviation here, OAC. OAC, I'm going to make it minus. So that is acetate. So when you see OAC, that's acetate. Now I'm going to write out I have to write out mercury acetate for the mechanism, and I'm going to write it like this. So one time it's ACO, and the other time it's OAC, right? Remember when you write structures, the way you write them, even just the letters, implies bonding. My oxygen has to be bonded to my mercury. So I can't just write OAC, OAC. I can't do it like this because that makes it look like the carbon of my acetate is what's bonded to the mercury, where actually it's the oxygen. So I can flip it around and go ACO, and that implies the oxygen is bonded to the mercury. That makes sense? That's why it gets flipped around. So now they're all in the same place. So we have our double bond, right? And then I have my mercury, my mercury acetate. So they want to make an A for some reason. So our pi bond can add to the mercury and push an acetate off. Now we can think of mercury as just a great big poisonous bromine, right? So just like when you added your double bond to your bromine, the bromine used its lone pairs to add back to the positive charge it was forming. Mercury is going to do the exact same thing, right? So I'm going to make a 3-membered ring with a mercury in it. This looks suspiciously like a bromonium ion, right? 3-membered ring, positive charge. We know what to do with those if there's water around, right? So now the water that was in the reaction can add to the most substituted carbon of this 3-membered ring, because that's the carbon that's most positive, push electrons onto the mercury, and I'm going to end up with so I've got this oxygen with a positive charge that has an extra proton on it. Again, you've seen something very similar to this before. You got to have a sense of what to do with it, right? Now I need to have another water molecule come by and grab that extra proton, just like at the end of the hydration mechanism or the end of the halohydrogen synthesis. So I'm going to redraw this structure. Have another water molecule come by. Grab that proton, push electrons over. We're going to generate H3O+. And that's the end of step 1. Right, so that first step of our 2-step procedure adds our alcohol, but leaves us with a mercury on our molecule. Right, the second step is removing that mercury. Now, I super duper shortcut this step, right? So we're going to take this. This is now step 2. We add sodium borohydride. And for right now, all you need to know is that sodium borohydride is a source of H minus. It just gives us H minus. I'm not going to worry about the structure of sodium borohydride. I'm just going to say it gives us H minus, and that H minus knocks the mercury off of the molecule. To give us our alcohol minus the big poisonous ball of mercury on the end. And as I told the earlier class, is this all the arrows for this step? No. Is that all the arrows that you need? Yes, you are good. I super shortcut this because there's more stuff involved. But just think, hydride knocks off the mercury acetate. I don't have the hydroxide in there. The hydroxide kind of makes a mercury hydroxide eventually, but we're not going to worry about that. Just know sodium borohydride, that hydrogen knocks off the mercury. So again, what's great about this is you never have to worry about any rearrangements. It just is always the simplest answer of alcohol on the most substituted carbon, hydrogen on the least substituted carbon. So if I did this, right, I'd end up with a ring expansion, lots of sadness, right, but I get that. Move my carbocation. Then add water. Get that. A lot of work, a lot of size. What if I really wanted that 4-membered ring with an alcohol beside it? Right? That's where using mercury acetate comes in. You can just use that. You don't have to worry about any rearrangements. If you just add I'm one time going to make the arrow long enough and not have to redraw it. This was clearly not that time. Right? No rearrangement to worry about. Nothing tricky. Just put the alcohol on the most substituted carbon of the double bond. Super straightforward. So for the acid catalyzed hydrations, right, we could also use an alcohol to start with, right? So instead of using water and making an alcohol, we could use an alcohol and make an ether. So right, use an alcohol with sulfuric acid. You make an ether. I can do the same thing with an oxymercuration, but I can't use mercury acetate. I have to change the mercury salt that I use. So I want to do this with mercury. long arrow, mercury, OTFA, 2, alcohol, THF, and again, sodium borohydride, hydroxide, and that will make an ether. So OTFA is a variant of acetate where you've replaced all the hydrogens on acetate with fluorines. So if I go OTFA, that is that which is trifluoroacetate, right? TFA, TFA. So I can't add alcohols to double bonds using mercury acetate. I have to use mercury trifluoroacetate. So why do I have to use the two different reagents, right? So we have to think about our nucleophiles first. And the first thing to know is that water is more nucleophilic than alcohol. So just in general, water is more nucleophilic than alcohol. So water is able to add to electrophiles better, right? So you don't need to be as reactive as an electrophile for water to add to you. So water can add to less reactive electrophiles than alcohols can, right? So I can't change how reactive an alcohol is. That's kind of like the reactivity of ethanol is the reactivity of ethanol. That's baked in. I can't change it. What I can change is I can change my electrophile, right? So when you do these reactions with mercury acetate and mercury trifluoroacetate, you're going to get to something that looks very similar in both cases, right? The three-membered ring with the mercury. And the only difference is one has an acetate on it and one has a trifluoroacetate on it. Fluorine is electronegative, right? So it pulls electrons towards itself. So when it pulls electrons towards itself, it's pulling electrons away from other atoms. So with those three fluorines on the end, you're pulling electrons away from the mercury, right? And then in turn, the mercury is like, hey, I'm going to pull my electrons closer to me, which pulls electrons away from the carbon. So having the TFA makes this carbon more positive than that carbon, right? So right, so the TFA pulls electrons towards it, makes the carbons on the three-membered ring more positive than if it were an acetate, right? So if you have an alcohol, right, the alcohol can't add to this, right? That carbon isn't positive enough for the alcohol to add to, right? But because I have trifluoroacetate on the other structure, the alcohol is able to add to this carbon. I've made the mercury complex more reactive. I was stuck with the alcohol's reactivity, But the thing I could change is I could make my mercury structure more reactive by putting the trifluoroacetate on it, and that made it so the alcohol could add to it. Where since water is more reactive than alcohol, water can add to this. I don't have to add anything extra to it, but I can add something extra to it to make alcohols react. So I'm just changing the intermediate's reactivity. I'm changing how reactive the mercury complex is so that my alcohols can react. Seem good? These reactions are I'm going to do just step one. So step one of this process is an anti-addition, right? The oxygen ends up on one side, the mercury ends up on the other, which is what you would expect based on the mechanism, right? Because it's just like making a halohydrin. That's an anti-addition. This is an anti-addition as well. We don't ever show the stereochemistry in the product because in step two, we get rid of the stereochemistry here, right? We replace that with a hydrogen, and so I no longer have two chiral centers. So I no longer have relative stereochemistry, right? Because I can only have relative stereochemistry between two chiral carbons. And this is racemic. It's a one-to-one mixture of R and S. So you just don't need to show any stereochemistry for it. That makes sense? Since I don't have two chiral centers, since I don't have another chiral center to compare to, it doesn't matter if it's a wedge or a dash because it's a one-to-one mixture. So even though the first step's an anti-addition, we never end up showing stereochemistry in the product because this step here gets rid of the second chiral center. We never show stereochemistry in a product.
So I was asked here what the point of all these reagents were, why we were using all of this stuff.
Yes, so this whole two-step, let me go back. This whole two-step process, right, this just adds, in this case, an oxygen, just adds one oxygen and a hydrogen to the molecule. So we're doing a whole bunch of stuff to just add an OH and an H, to just add water across the double bond. But we're doing it this way so we don't make carbocations, so we don't have to worry about rearrangements. Sure. Okay. So hopefully everyone watched the super long video that involved the super long mechanism of hydroboration, right? Because my child's daycare is celebrating Indigenous Peoples Day or whatever. That's the alternate name for Columbus Day. So you should have already watched that. So you look at this and you know exactly what's going on. Right? You're like, oh, this is a hydroboration. It is an anti-Markovnikov addition, which means the hydrogen goes on the most substituted carbon, and the other thing that I add goes on the least substituted carbon. And this is how you make the less substituted alcohol from a double bond. Right? Of course, you all know that. It's not a big deal because you watched the video. Again, I have full faith that you watched it on your Thursday night. You're like, the coop? Nah. Organic videos? Ah. What's that lady? Like the meme lady? Yeah. Right. Yeah, you couldn't see that my chin scrunched up because, I have no chin. I'm just cloth from like the eyes down, as we all are now. Right. So hopefully you know all that. What I'm going to pick up with, where we're going to kind of start from that, is we're going to go all the way to slide 28, right? So we're going to talk about radical halogenations. Of double bonds, right? Oops. Where you take HBr, hydrogen peroxide, and light, and that lets you add the bromine to the less substituted side of the double bond. Right? Someone got a physics minor, got to flex on it every so often. So I always end up writing H nu, right? Which is, H nu equals the wavelength of light. Ta-da, physics. But then I can't ever find the nu on my computer without like going through like control and just hitting all of the buttons until I find it. So just I end up typing light because it saves me time. So you'll see me write it as H nu or just as light, 6 to 1, half dozen of the other. Right? And that will put your bromine on the less substituted carbon of your double bond. Radical reactions, every radical reaction has 3 parts to it. The first step is initiation. The initiation step is a step that makes the first radical for your reaction. Right, so this is where you have no radical, this makes your radical. This initiates the process. Then you have step 2. Right? That is the propagation step. Each step in the mechanism makes a new radical. The propagation steps, this is where your products are formed. So when you're like drawing out the reaction, you are anticipating that the propagation step is where you're going to make your products. You can make products in the termination step, but that's usually like by accident. So like 99% of the products that you're going to make, of the product that you want, comes from propagation, and maybe there's a little bit from termination. And then termination, In termination, two radicals, like that's not even like close to a word. Two radicals. I don't know what that was. That was rough. That was rough. The Zoom people are like, it's bad enough that I'm like sitting on my couch right now. The man came and makes shapes that look like letters. Okay, we topped out. 18 people showed up today. Good job, 18 people. Good job. All right. So termination is where two radicals that you've generated in your reaction run into each other. It's random. It's just accidentally two radicals got close enough together and they reacted. Right? You make side products here. So this is where you just kind of get like random products that you don't really want, but are just the result of two radicals got too close together and reacted, and the reaction wasn't doing what you wanted. So radical reactions are often called radical chain reactions, because once you start the initiation step, the reaction just goes. It just keeps going, and the radical keeps regenerating itself through the propagation step, basically until you run out of things that can make radicals, right? Or if somehow all your radicals smash into each other in a termination step, and you end up making things and not making new radicals. All right. So let's talk briefly about arrows. You're going to see, it might be in the video, but you're going to see a new arrow, right? So we've got this arrow, our good friend. I'll make him red because he's always red. Right, this is a double-headed arrow, right? The end has two heads. It looks like a regular normal arrow. Double-headed arrows show the movement of two electrons. So every mechanism we've drawn up to this point used a double-headed arrow because we were showing two electrons moving, right? A negative charge, a pi bond, those are all consist of two electrons. Radicals are an unpaired electron. So you're just showing the movement of one electron with a radical. So for radicals, we use a single-headed arrow, which is sometimes just called a fishhook arrow because it kind of looks like a fishhook, right? These show the movement of one electron. So whenever you're doing a radical mechanism, you need to use the single-headed arrows because that's showing one electron moving. So that's how you can differentiate when you look at a mechanism. Is this a radical mechanism or is this, a regular like positive, negative charge kind of mechanism? Is by the type of arrow. So for our reaction that we had, right, this with HBr, H2O2, again, my sketchy physics degree or physics minor, right? I put the bromine on the least substituted carbon, hydrogen on the most substituted carbon. The initiation step to make our first radical right? You take hydrogen peroxide and you shine light on it. Now, I could ask someone on Zoom to go get a bottle of peroxide to show us, right? Because we should do scavenger hunts if you're at home, right? But every bottle of peroxide you've ever bought in your life, the bottle was brown, right? The reason is oxygen-oxygen bonds are really weak. So the energy from light is enough energy to cause an oxygen-oxygen bond to break. And you have one electron go on one oxygen and one electron go on the other. Right? So you generate two hydroxyl radicals. Now, oxygen radicals aren't very stable because oxygen is electronegative. It wants electrons. And you can think of radicals as radicals are kind of like they're atoms that are short an electron, right? They're not a carbocation because there's one electron in that orbital, but it's short of having all of them. Yes.
I was asked here if there's a difference between writing HO dot or dot OH.
There is not a reason. This versus this are the same thing, right? I did that in the early class, and someone's like, he's just trying to get in the Christmas spirit first, early. It's like, yeah, that's right. I'm Target. Like, I have my Christmas decorations up in my head already. I'm just like, ho, ho, ho. Like, screw you, Halloween. Screw you, Thanksgiving. Christmas. Go. And again, like, Halloween's going to suck this year. Like, we should do reverse Halloween, right? Where people drive around and just throw candy at children. That way, like, socially distanced, right? It could be fun you can keep score. Like, hey, hitting a 4-year-old in the head, that's 50 points. Good job. Next. I think that's solid, Zoom. Like, you can't argue with this. Think about how much more fun Halloween would be if you just, like, walked out in your front yard and got hit with 3 candy bars. You'd be like, this is the greatest day ever. I had to do no work, and I just got hit with food? Sweet. There is a downside. When I was a kid, like, I was like 5. In the little West Virginia town I was in, we had a parade, and they had fire trucks, and they would throw candy off the fire trucks, right? And there was a little piece of gum that was going to get run over by a fire truck. So I ran out into the street, stuck my hand under a tire, and ripped it out. My grandmother was almost died. I got that piece of candy, that 5-cent piece of gum. I might have risked my hand for it, but I got it. Closest I ever was to being Indiana Jones. Like right there in that instant. Great. Okay. So anyway, I make hydroxy radicals. These are really reactive because oxygen wants to have a full octet of electrons, and it's short one electron. So what happens is this hydroxy radical will react with HBr, and you'll make water. I'll do it this way. Oh, that's right. Plus a bromine radical. Right, so you would much rather have a bromine radical than an oxygen radical, right? Oxygen is the second most electronegative element on the periodic table, so it's really mad that it doesn't have all 8 electrons around it. Bromine's got like, math, I don't know, 70-something electrons around it. It doesn't know. It loses one, it gains one. Whatever, man. My life's good. It's got a bunch of electrons, right? So this is the radical needed for, oops, those aren't letters, again, for propagation. Right, so the initiation step, the whole point of initiation is to get us to this bromine radical. And since I didn't turn this lecture into a complete and total dumpster fire, we're done a little bit early. So this is where I stopped in the first class. We'll pick up propagation and termination on Wednesday.